So last day we learned about how whenever you have a wire and it moves within a magnetic field, a current is produced. So just to recap, because there's a lot going on here, we learnt first of all about the electric motor. And remember, with the electric motor, you're changing electrical energy into mechanical energy, and by that I mean movement energy. So the input, I suppose, to an electrical motor is that you have an electricity supply. You are providing the electrical current in that case. This, however, the AC generator, is the opposite. So in this case, we are taking something which is moving and we're using that movement to produce electricity. So we're taking mechanical energy and we're changing it into electrical energy. So the two things are complete opposites of each other. And I think sometimes, especially with the, I know you can't watch them, but the wee animations that we show in school, I think sometimes that is a wee bit lost. So I just want to reiterate that. The two things, the motor and the AC generator, are exact opposites of each other. So the motor takes electrical energy, changes it into mechanical energy. This one takes mechanical energy and changes it into electrical energy. Now, just to remind you, whenever you move a wire in a magnetic field, a current is induced, so a current starts to flow in it. And if we have that set up in a very clever way, it means that we can use that principle to get a continuous supply of electrical current. So we're going to work our way through these. These are the wee snapshots of the animation that I would be showing you if we were in school. And again, I've coloured in a little bit to try and help explain what I'm talking about. And I've written in the descriptions and everything here. First of all, the first thing I want you to write in is that a force is required to turn the coil. So I mentioned at the very end of last lesson that this is what's going on inside electrical power stations. So if you think, say we have a fossil fuel power station, so if we are burning coal to heat up water to produce steam, the steam turns a turbine, turbine turns a generator. So that is where the movement energy is coming from in this. Or if it's a wind turbine, the wind is turning the turbine, which is turning the generator. And then an electrical current gets produced. Now, first thing I want you to write in here before I go, I'm going to go back up here and explain what's going on. Can you just write in this? So this is basically what we were learning last day anyways. When the coil rotates within the magnetic field, current is induced. Right, write that in. Okay, now, where am I? Let me fix this a wee bit. Now, we can use Fleming's right hand rule to find the direction that the current is actually flowing. And no, I haven't got that wrong. Whenever we're using the electrical motor, we use Fleming's left hand rule. Fleming's right hand rule, because they're opposite effects, we use the opposite hands. We use Fleming's right hand rule to figure out the direction of the current. The three things stand for the same thing. So first finger, magnetic field; second finger, the direction of the current; and the third finger, or sorry, your thumb, is the force or the thrust. Okay, so if we look here, so I'm going to pretend that these wee arrows showing me the direction of this current aren't here. And this one, can you see this? This arrow here is showing the direction that this is rotating in. So this is rotating clockwise, okay? So if I look at what's going to be easier for me, neither, I don't think. Let's look at the yellow side, the side I've coloured in yellow. So if I put my first finger in the direction of the magnetic field, thumb in the direction of the force. So if this side's going up, this side must be going down. So I've almost got it there. Oh, you cannot see that at all. I've got my first finger in the field, north to south. Thumb is pointing down, and my second finger is pointing out, like towards me. So that tells me that the current here is coming out and along here. Now I know that's already marked on your diagram, but I just wanted to show you where that came from. Now do me a favour, see the way I've coloured in this yellow, and I've coloured in the commutator that this bit of the coil is connected to yellow. That is to help us later on this lesson understand why we end up with alternating current as opposed to direct current. Okay, so if you remember, we get our maximum current being induced whenever the whenever the coil is cutting across perpendicularly. So here, with the current traveling this direction, we've got a slight positive current. Okay, let's look at the next three diagrams. So step 2 over the page. See now that this is horizontal, we still have the current has gone from this to this. So now that it's horizontal, we've got the maximum magnitude of current. And this is just the same side of coloured yellow the whole way through this. Okay, so the wee description that I want you to write in there, when the coil is horizontal like this and still moving is key. The wire is cutting across the lines of flux or magnetic field lines perpendicularly. I wasn't sure if that was a real word. So the magnitude of the current is maximum. Okay, so this is exactly the same as the one we just looked at there, but it's just rotated around a wee bit more. So now we have a maximum value of current because it's cutting across perpendicular. So this is going to keep on rotating around, and then the next stage shows it whenever it gets to the vertical position. So over onto 232. Now the side that was over here is down around here, and because the coil is not cutting across the lines of flux anymore, there's no current induced. So our wee ammeter is showing a 0 current. So get that in, colour that in, then we can go on. Right, this bit here I think I'm going to find the hardest to get across to you. Okay, so on page 233 now, we're at step 4. Before I show you what I've done, what I've written up here and stuff, can you just write this in for me? So as it keeps rotating, current is induced in the opposite direction, and you'll see there that now our current is going the other way. And I'm going to try and explain to you why that is the case. As long as you know it is the case, I'm happy enough. Like, as long as you know as this rotates, the current getting produced is constantly changing direction, that is enough. But wouldn't it be great if we understood why? Okay, now the reason why is all because of this really clever wee design here. So the side that I was colouring in yellow, remember it started off here, came down here, rotated around here, now it's here. But this bit that we have been looking at the whole time, it's always like it's connected to that front commutator, and because of this nifty little situation, that is why we end up can't get my sentences out. That is why the current ends up like constantly changing direction. Okay, so if I go back to step 1, here it is, here. Yeah, right. So if I go back to step 1, see the way we did our right hand rule, we figured out the current was coming out here. Well, this front commutator is connected, so it comes around this way. Right? Happy? Take my word for it. Now this bit here, because the we'll do Fleming's right hand rule to figure it out. So right hand first in the direction of the field, this way. Thumb in the direction of the force, so the force on this side is going up, so my current is going in on this side, and you can see those wee arrows have that marked on. So now my current is going along this way, which is the way it was going before, I know, but because of these connections, this bit is connected to this front commutator, and now it's going here. And if we compare those, can I put these both in? Yeah, if we compare those, if I look at these ones, they're the opposite way, right? So whenever this yellow bit was on this side, because it's connected to this front commutator, then the current we figured out using Fleming's right hand rule came along here, blah blah blah, along there. By the time it's done, it's gone like 180 degrees now. Current here is going in, so traveling along there. And now this one here, the side I haven't coloured in, is always connected to this front commutator. So now the current travels around in the opposite direction, which is why we have that wee negative there. Now, I just wrote on there, follow these connections to understand the change in direction of current. To be honest, I've got through that much quicker than I thought I would, so now I'm worried I haven't explained it very well to you. Tell you what, if you watch this, obviously hopefully you are, and have a good proper think about it and see can you follow what I'm on about with the one side I've coloured in and the side I haven't coloured in, and then do make sure you ask me, because we can spend more time going back over this if needs be. Okay, because I do feel like I ended up rushing that, I don't know. Right, we've one more page to fill in. Right, so we've got a graph of the voltage that's being produced. Now I know I've been talking about current so far, but whenever you've got current, you're going to have a voltage. So like V equals IR, do you remember? The two things are directly proportional to each other. So if we were to plot the voltage produced by an AC generator, we're going to get a graph that looks like this. Okay, now stage one, I'm really failing on the diagrams recently. I've tried to draw what this is here. This bit here is the magnet, the bit around the outside, and then this is supposed to be the wee coil. So this is me trying to draw the coil sitting vertically, and then this is the coil sitting horizontally. They're the only two I drew because this just repeats over and over again. So stage one, the coil is vertical, so it's not cutting across those lines of flux, so no current and therefore no voltage is produced. Stage two is by the time it's rotated round and now the coil is horizontal. So whenever it's horizontal, you're getting your maximum current, which means you're getting your maximum voltage induced. So that's here. And then 3 is back to this again whenever the coil is vertical. So we've got no voltage. 4, the coil is horizontal, but it's like the other way around. So our current is now the opposite direction. Sorry, and our voltage. And then 5, our coil is back to being vertical again. So there's no voltage induced. So pause and get that wee bit written down as well. Okay, and then again, before I show you that, the size of the induced voltage can be increased. You could nearly come up with these yourselves. Okay, rotating the coil faster, you're going to get more voltage and current. I'm probably going to keep saying current by mistake here. If you have a stronger magnet, you're going to have a stronger magnetic field, you're going to get more current, therefore more voltage. If you've got a coil with more turns, why have I written no turns there? Sorry, that's better. So using a coil with more turns and then wrapping the coil around a soft iron core, it's going to increase the voltage that is produced as well. Right, promise me you'll have a proper think about that, and then because I'm going to be asking to see your notes, you can add a wee comment on there if you need any more help. If you want, I can then like reply in the comments with the wee voice note thing, or I can do another video if enough of us need it. Okay, that is us. That was actually worryingly quick, so that's me. I'll see you. Bye.